Good morning, ladies and gentlemen. Welcome here to the technical forum of the group exhibit Hydrogen Fuel Cells and Batteries. Very happy to see it as full as it is, but we still have some seats here. So please come closer, have a coffee, have a tea on the house, and listen to our next presentation, which will be held by Dr. Eva Ravn Nielsen. She is Center Manager of DTU Energy, Fuel Cell and Hydrogen Test Center. She's coming from Roskilde in Denmark, and she will talk about European fuel cell and electrolysis activities, testing, test procedures, and demonstration projects. I'm looking forward to that, Eva. Here's your stage.
Thank you very much. Yeah, I brought 27 slides for these approximately 17 minutes, so I will have to go through quickly. I will tell you about our test center, FCH Test Center for Fuel Cell and Hydrogen Technologies, about the testing that we perform, and I will let you know about the standardization of test procedures that we are involved in, and other projects, demonstration projects, that are new to some of you. The FCH Test Center is part of a Department of Energy Conversion and Storage, which we call DTU Energy, part of the Technical University of Denmark. We are based, as I said in the introduction, in Roskilde in Denmark, outside of Copenhagen. And we are 230 employees and around 100 working with fuel cells, electrolysis, and batteries. We have done fuel cell research and development for almost 30 years now, mainly in ceramic fuel cells, but also in PEM fuel cells and other types. And we are offering companies, organizations, testing on commercial terms through the FCH Test Center, which we represent here at the Hannover Messe. DTU Energy focus much on industrial collaboration, and the research we do, we focus that the methods used can be scaled up later, so it will be industrial relevant. We work very much on materials and components level. We come out of our materials research department, but we increasingly focus on also stacks, small systems, prototypes, and system analysis as well. We are specialized in advanced testing, and I will tell you about some of our test methods, characterization of materials, and do also a bit of modeling. The test center works on testing, training of technicians and engineers, how to perform tests, consultancy, and a lot of project work, which I will tell you about here. One of the specialized testing test methods that we do is the electrochemical characterization. We do current voltage characteristics and also electrochemical impedance spectroscopy. And we have, over the years, refined this method very much. So, especially in solid oxide fuel cells and electrolysis cells, we can interpret the results so that we know from each layer, each subcomponent in a fuel cell, which one is responsible for the resistance we see. And when we measure before and after a long test, we can also say which part of the cell is the degradation is due to one part or the other. We can say, would this be due to too little porosity, so the gas diffusion is hindered? And we do this on cells, and we do this on stacks as well, where we have really good results, low noise measurements. The electrochemists in our department work closely into action with the microscopists. So after making fuel cell tests, the cells are then usually handed over to the microscopists. So they characterize and they sometimes confirm, sometimes give added explanations of why the performance is as it is. And then we hand it over to the process development guys and girls. So they can say, okay, you need more porosity. We can change and develop the production method so that we get for example, the porosity that is required for this application. So that interaction between disciplines is the strong point in our department. We offer corrosion testing of interconnect. We can measure at the right relevant temperatures, the right atmosphere, and we can test a number of components at the same time so that you get a lot of results. We measure the area-specific resistance, so the resistance of these interconnect plates, how does that develop in time? And the second last method I will tell you about is mechanical testing, where we have made a test setup where we can measure ceramic materials or other materials, their strength, and we can measure again at the relevant conditions. So we have built a furnace. We can heat up to 750 or 800 degrees, which are the relevant temperatures for ceramic fuel cells. We can apply the right interesting atmosphere, so we can make a hydrogen atmosphere surrounding, and then measure the strength. And we can measure 17 samples in one go. And for reliable mechanical results, you need a lot of samples because some are fragile, some have flaws. So in order to get reliable results, you have to at least to break 30 samples and measure the strength of each. So in our test setup, we can do that in 2 goes. And as far as I know, it's the only place in the world where we can get reliable results that fast. And finally, we do a high-pressure testing of cells and stacks. And they can run in electrolysis mode or fuel cell mode. We're now up to 30 bar, but our equipment is prepared to go up to 50 and 100 bar. Lately years, we have been involved in projects on standardization of test procedures. And it becomes increasingly important that the test procedures used in the laboratories reflect the real use in the applications afterwards. And that they are reliable, so that in the fuel cell business, we don't get the experience that the testing in the laboratory suddenly was totally different of real use of the technology. We are in the ongoing SOCTESQA project, dealing with solid oxide fuel cells and electrolysis cells and stacks, and also combined operation of these two. We are 7 test institutes involved, and we compare our results so that we know that also across laboratories the results will be reliable. And we make sure to interact closely with industry, so the methods and conditions that we determine will be as close and relevant to the real application as possible. We are focusing on 3 applications, or actually 4. In solid oxide fuel cell mode, we look into micro CHP applications and APU. For electrolysis mode, we look into power-to-gas applications. And for the new combined operation of SOFC and SOEC, we have the power-to-gas-to-power balancing of electricity network application in mind. We base our test programs on a number of test modules. We will suggest final programs to follow, but if in your lab something else is relevant, then you can pick the modules, that small pieces of the program, and still refer to this test procedures, but saying, okay, I do the startup, I do a current voltage characteristics, and then I go to measuring the temperature sensitivity, and then I would go to operation under varying current, and the relevant in my lab might be then to shut down. So you can design your own test program, but still based on the standardized test modules. Some of the first results where we are comparing across laboratories, these are just the simple results of a current voltage curve, show that also the stacks that we are testing are pretty similar because the curves are very much on top of each other. It's the same. Only when we go to high current, we see small deviations. And we are, of course, looking into the reasons for these differences and improving. One thing we found very early in the project is the temperature of the stack and also temperature of the gas going into the stack is very important to control very fine. And where you measure that temperature does make a whole lot of difference. So these are things that will also be defined in our test programs. As I mentioned, we try to mimic real applications as close as possible. And this figure I will show you to illustrate one of the applications, the combined operation. It can be used when you have sometimes a lot of wind power, sometimes more than you need, and other times you have electricity deficit. And these are actually real life curves from a Danish island called Ærø over 16 days, that sometimes the blue curve is higher than the red, which is the need of electricity, and some days the wind turbines generate too little. So when we have a surplus of electricity, we can run the electrolysis and produce hydrogen or other substances. And when we are in need of electricity, we feed gas into the fuel cell. And the same unit can be used in both modes. This curve we then simplify to, a curve that can be used in a laboratory, even a laboratory not very well equipped with automatic control. So we run, this is the solar profile, and I think we reflect Denmark, so that will be 6 hours of sunshine where we have a lot of electricity and run electrolysis mode, and then rest of the day and night we run fuel cell mode. And this we are alternating and measuring also the voltage and the current. And this we do for a number of days, so see how the stack or the cell react to this. So this way we define test programs for each application. We have also been involved in the PEM stack test project, which was finalized last September, which was very much about the same topics, but this time concerning PEM fuel cell stacks. And again, application-specific programs have been developed regarding performance, endurance, and safety when running a fuel cell stack. And for the endurance, 3 modules were developed on continuous operation, load cycling, and start-stop cycles. All these programs and modules are available to the public, and you can go to the website here, and you can find the presentations later on the Messe website. If you are interested in getting the resulting programs and modules from this project. Then I will mention demonstration projects. We are involved in the ene.field, large European demonstration of micro CHP units across Europe. Up to 1,000 units will be installed that can supply a house with power and heat. The project lasts for 5 years, and we are involved with the analysis of the data coming out of it. This is the project consortium. It gathers 8 or 9 manufacturers of these heat and power systems, and it's rather unique that they work so well together. They are competitors, but they know they have to work together to get these new technologies to the market as soon as possible. And then they are assisted by a number of research institutes, and DTU is one of them. The project comes out with a number of reports. These are available from the project website. And since Monday, we also have knowledge report out on the non-economic barriers to mass uptake of this new technology. We also have smart grid capability, regulation codes and standards, supply chain analysis, and an analysis of the education needed for installers and technicians in the field. The findings and conclusions from ene.field, very brief, is a successful installation of more than 500 fuel cells by now in a range of house types and across 8 European countries. Germany has clearly shown to be the strongest early market because it is more favorable financial and with local regional funding support. And that is also the reason why the manufacturers and installation companies in Germany are also more mature than in the rest of Europe. The fuel cells are ready to be implemented in a smart grid. They can be remotely controlled and adjust up and down in power. They are still quite expensive, and we see how the cost can go down is when we scale up in production volume. That will allow both more efficient production and also more efficient outsourcing of components. And here is the ene.field.eu website where you can get all these reports and more information. We will be involved with a number of other EU projects starting here 1st of May and 1st of June, which will involve both electrolysis technologies and fuel cell technologies. So we are a partner for assisting companies in these consortia on data collection and analysis and reporting. You can contact us here at the Messe. We are Carsten Prag, my colleague, Carl, and myself. We are at booth D62. And I want to thank you all for your attention.
And we want to thank you for these wonderful presentations. And there might be some questions right now, so please raise your hand. There's a question at the moment. Just one little question, Eva. This project with the SOFC and SOEC together, it's not in the same device, or is it possible, a reversible device?
It is the same device.
Oh, really?
And we are testing both on cell level and on stack level, and we prove that it works. And I believe that some of the companies are also showing this in 50 kilowatt scale.
Yeah.
And our findings are that the degradation is actually lower when you alternate the operation mode.
The fuel cell likes it to be electrolyzers once in a while.
Like
okay.
Cleaned once in a while.
Right. So how quick can you change from electrolyzers to fuel cell then?
It depends on your system. You have to change the gas flow as well when you change the current. Sure. So how much flow is it? Can you remove the steam when there's too much steam going from one mode to another?
Yeah.
You can do it in 5 minutes,
okay.
but you can also you can adjust from a high power output to a lower power output. Only when switching completely from one mode to another, you might need minutes, maybe 1 hour, half an hour idle time before you change to a different mode.
And it runs at the same temperature as electrolyzer and as fuel cell?
It does, and you can use similar gases so that you have hydrogen and steam present in both modes.
That's very interesting indeed, Eva. Very nice. Any more questions from your side? Then please give her a big hand once again. Thank you very much for this wonderful presentation. The next presentation will come up in 1 minute. Just give us a minute to prepare the next live streaming here in our technical forum. It will be about reliable fuel cell stack characterization. Ulf Groß is already here. He's head of department fuel cell system from Fraunhofer Institute for Solar Energy Systems. So we will start in 1 minute time.